So, good morning everyone. It is a pleasure to be here with you, talking in this seminar series, Quantum Matter Meets Math. And today I'm going to talk about quite a fresh topic, which is called localization, anisotropy, and the complex geometry of two-dimensional insulators. Okay, so here is the outline of my talk. First, I will begin by talking about some generalities about insulators and metals. Then I will talk about the geometry of threading a flux through the system in the case of band insulators. I will talk about the quantum metric in twist angle space, the localization tensor and the complex structure tau. And then I will make contact to the low energy theory near a quantum phase transition and the geometric character of tau. I will proceed by giving an example, that of a modified massive Dirac model, and then I will provide some conclusions and an outlook. Okay. So, insulators and metals. Here is an illustration of what in band theory insulators and metals look like. On the left, and by simplicity, I took an example with the two bands. So you have energy as a function of momentum, and you have, since we're talking about fermions, you have a Fermi level, which I denote by EF. And then the difference goes as follows. So in the left, you have an insulator, and in the right, you have a metal. The ground state of the theory is obtained by filling all the states which are below the Fermi level. And the difference goes like this. So in the left, you have a gap to the other band because the Fermi level is here and you have this energy gap. And on the right, by inserting an infinitesimal energy to the system, you can excite electrons because there is no gap, okay? So this band here, the blue bands, I will call them the valence bands, and the red bands, I will call them the conduction bands. And even in the case of an insulator, you could, in principle, give an energy amount which is sufficient to excite, which is of the order of the gap, okay? Okay, so now a bit about the phenomenology of the insulating state. So intuition tells us that the insulating character of a system of electrons has to do with the way these are organized in space. If the electrons are able to move in every direction, then if I turn on an external electric field, I will generate a current which is parallel, longitudinal, to this electric field. Okay? So this is the case of a metal. However, if the electrons are localized, if I apply an electric field, in general, I will not, intuitively, I will not produce a longitudinal current. Okay, so translating this into equations, the property of electrons being in an insulating state is related to this tensor, which is called the conductivity tensor. And when I apply a uniform external electric field, I will have a current as given in linear response theory, which is a linear combination of the components of the electric field. So, as a preliminary definition, I would say that an insulator has zero direct current conductivity. To be more precise, the symmetric part of this tensor at zero temperature is zero, while a metal has a non-zero direct current conductivity. This is not a full story, as in the antisymmetric part of the conductivity describes the transverse conductivity, and it is responsible for what we know as the anomalous Hall effect. More on that later. Actually, the intuition concerning electron localization is correct, as the conductivity tensor can be explicitly related to the so-called localization tensor, this object here, which has to do with the position-position two-point correlation function. Here x mu denotes the center of mass position operator, and this average here is the ground state expectation value. Okay. So if we have an insulator, this quantity here is finite, and if we have a metal, it will blow up. Okay. So now I can proceed to the systems I will consider, and in particular, let us consider the geometry of threading a flux through the system for the case of band insulators. This is a very specific thing. Okay, so here's the setup. We have a system of fermions on a two-dimensional lattice with periodic boundary conditions. The period on each direction is n is a natural number, and later we will take n going to the limit n to infinity, which is the thermodynamic limit. Okay, so this is the system we are considering. You have this full lattice here, and I'm going to select this n by n square, and I'm going to identify 0 with n and 0 with n. Okay, this is the position space. Because I did these identifications, topologically the positions of the fermions are taking values in the two torus. We can thread fluxes associated with the generators of the fundamental group of the torus, that is, the loops which are not contractible to a point. Basically, this means that if I adiabatically move the fermions around these loops, they will get some phases, okay? Importantly, this does not introduce a magnetic field in the system, because basically this corresponds to adding twisted boundary conditions to the wave functions. Okay, so here is our modified picture. So now we have this little square, this fundamental square, and as the fermions go around the fundamental loops, this here and that here, they will get phases phi 1 and phi 2. In the thermodynamic limit, the real space becomes the lattice Z2, meaning when I take n going to infinity, and the allowed momenta live in the Brillouin zone, which itself is topologically a torus. To see this, we consider the following plane waves, and we see that if r is the position taking values on the lattice, and if I take k and I shift it by a reciprocal lattice vector, I see that the plane waves are the same, so I'm instructed to identify k, which differ by dual lattice vectors. With the standard trivial boundary conditions for finite n, the allowed momenta for the fermions are explicitly given as follows. So they are 2 pi divided by n, and m is an element of this set here, so it takes values in 0 to n minus 1 Cartesian product with itself. Okay, this should be understood as taking values on the Brillouin zone, and in the appropriate sense, as n goes to infinity, we recover the full Brillouin zone. However, when we thread a flux through the system, now the allowed momenta are shifted by the flux, basically the flux divided by n, and again, of course, we recover the Brillouin zone as n goes to infinity. So here is a picture of what it looks like. The black points here are essentially the positions, the momenta allowed for zero flux. And when I turn on the flux, you have the red dots, which are the new allowed momenta. And now notice the following, that as I change the flux here, notice that the flux swipes this little square here. I recover the full Brillouin zone. And moreover, if I change the flux by 2 pi times an element of Z2, I recover the same points, and therefore the system has recovered, has gone back to itself. So the theory is actually the same. Okay. So now let us consider tight binding free fermion models. The simplest example is perhaps a 1D chain with no internal degrees of freedom and with nearest neighbor hoppings. So this is something like that. This is the single particle Hamiltonian. And I can go to momentum space, and this is diagonal. And this is the spectrum of my tight binding model. Okay? In second quantization language, this corresponds to this Hamiltonian, where psi and psi dagger are fermionic annihilation and creation operators. So this is for 1D. And for the case we're interested in 2D, if I have a translation invariant charge preserving setup, which is what I'm interested in two spatial dimensions, I will have a Hamiltonian in second quantization, which looks like that, where now the psi daggers are an array of fermion creation operators, and the indices, which go from 1 to n, correspond to internal degrees of freedom, such as pseudo-spin, spin, whatever you can think about. And h of k is an n by n Hermitian matrix, which essentially corresponds to the action of my second quantized Hamiltonian in the single particle sector. Okay? If the hoppings in real space decay fast enough, then this assignment, which takes a momentum k in the Brillouin zone to the matrix h of k, is smooth. Assume that we are in an insulating state, so that we have bands below the Fermi level and bands above the Fermi level. The bands below, as I said before, are the valence bands, and the bands above are the conduction bands. Then I have naturally defined a valence band projector, which is given by this expression. Theta here is the Heaviside step function. And here, essentially, what I'm going to take is the bands which are below the Fermi level. Okay? Okay. And this projector, because of the gap condition, is smooth. And it defines a vector bundle, which is called the Bloch bundle, over the Brillouin zone. Okay? What is this vector bundle? So I take an element k in the Brillouin zone, a momentum k, and over each k, I will take the vector space of eigenvectors with energy below the Fermi level, meaning that essentially I will take the vector space, which is the image of this projector at momentum k. Smoothness of P will guarantee the smoothness of this vector bundle E. So now let us see this in an illustration. So here I have a piece of the momentum space, which is globally a torus, but this is just a little piece. I have the momentum k, and over that k I have this vector space, which corresponds to the eigenspace, the direct sum of the eigenspaces with energy below the Fermi level at momentum k. Okay? And now observe that this vector space Ek is naturally a subspace of a fixed vector space Cn, because the matrix H of k is an n by n matrix. Okay? Now let's talk about the Berry connection, and more specifically about the microscopic Berry connection. Because each space Ek is a subspace of a fixed vector space Cn, we can define a notion of parallel transportation. Namely, we have a connection / covariant derivative on the vector bundle E to the Brillouin zone, which is essentially given by projection. So you take the derivative, or the exterior derivative, of your wave function in the single particle sector, and then you project. And this, of course, still is in the vector bundle E, or basically in the valence bands. And here psi of k is our single particle wave functions psi on the vector bundle E, which mathematically are sections of the vector bundle E. Okay? This connection is a microscopic Berry connection because it is seen by the single particle wave functions in momentum space in the valence band. Now, if I give you a local orthonormal basis for E provided by wave function psi I, where I runs from 1 to R, and R is the number of valence bands I am provided with, then because the Berry connection is compatible with the Hermitian inner product, I have a unitary gauge field, namely a UR gauge field, which is known as the Berry gauge field, and it is given by the following formula. And this here is essentially provided by the projection formula I gave you before. The Berry curvature is given by the exterior derivative of A plus A which A, as usual. And perhaps this is the expression more familiar to physicists, as a curl of A plus the commutator of the components of A. And of course, this is an R by R matrix because we're dealing with a non-abelian gauge field. Now, let us talk about the ground state of my theory. If we are considering the finite system with periodic boundary conditions, basically we are sampling the matrix H of k at the points of the form k equals to 2 pi over n times m, where m lives in this set, as I told you before. The ground state is obtained by filling the bands below the Fermi level, and this state will be constructed as follows. We forget about the periodicity of H of k in K, and we obtain a family of matrices in R2. Since R2 is contractible, we have global assignments K goes to Si of K in Cn, such that for each K they form an orthonormal basis of Ek. Since the SIs induced they are functions on R2, they will generically be multi-valued functions on the Brillouin zone. So notice that essentially this will not be functions on the vector bundle previously defined, but they will be multi-valued functions. The SIs give rise to creation operators, and this provides you with a Bogoliubov-Vallatan transformation. So you take the coefficients here that give you the expansion in the natural basis Cn, and you define these creation operators. These creation operators diagonalize the second quantized Hamiltonian. Now, the many-body ground state is at size n and periodic boundary conditions given by the Slater determinant formula. So essentially I fill the bands, the R bands, for every momentum k. And this here is the Fock vacuum. If I thread the flux with a twist angle phi, then I obtain a family of ground states parametrized by phi. Notice that the dependence on phi is explicitly given in the dependence of these creation operators on phi. Since the theory returns to itself because H of k is periodic, when I take phi and I sum it 2 pi times an element of Z2, we get a family of ground states parametrized by the twist angle torus. Now let us talk about the microscopic Berry connection. So at each flux phi, I attach a one-dimensional subspace of the many-body Hilbert space, which is generated by this ground state Gs of phi. What I have constructed now is a line bundle that is a collection of one-dimensional vector spaces over the twist angle torus. The Berry connection, which is defined as before through projection, but now with respect to the ground state Gs of phi, gives us a parallel transportation rule which is consistent with the adiabatic theorem of quantum mechanics. Now, the associated macroscopic gauge field is given like that. We refer to this connection as a macroscopic Berry connection because it is a property of the many-body ground state of the full theory. Now, the remarkable consequence of the Slater determinant ground state is that there is an intrinsic relation, an explicit relation between the macroscopic connection on the line bundle L and the macroscopic connection on the block bundle E. Namely, we have that the calligraphic A is 1 over n, the sum over all m's of the trace of the connection on E. You see? Moreover, the Berry curvature assumes this form here, and now notice, which is similar to that, it is a consequence of this formula. But now we have a factor of 1 over n squared. And this is very important, as you will see in the following. There are observable consequences to this formula. Namely, one can show that the transverse Hall conductivity, sigma xy, is I times the charge squared of the fermions, which we can consider to be electrons, at the Berry curvature, the macroscopic Berry curvature, at 0 flux. As we take the thermodynamic limit n, this Berry curvature, what appears here in the parenthesis, or this expression here, becomes a Riemann sum for this integral here. And what I have is that the Berry curvature becomes, in the n going to infinity limit, uniform in flux space, and the constant of proportionality is essentially the first Chern number of the block bundle E. And this is nothing more than the famous result of Thales and colleagues for the integer plateaus in the Hall effect. So the curvature became constant in the thermodynamic limit. Now you can ask, what about other quantities? Okay, so now I will talk about the quantum metric in twist angle space, the localization tensor, and the complex structure tau. So the family of ground states GS of phi, where phi belongs to the twist angle torus, provides a notion of infinitesimal distance between fluxes. It is given by considering the square of this overlap between the ground state at phi and the ground state of phi plus delta phi, where delta phi is an infinitesimal displacement. What I get is that I get 1, where in phi, because the states are considered to be normalized, and then I get this quadratic term, which corresponds to a metric in the flux space. The quantity here, G, capital G, is basically the pullback of the Fubini-Studi metric on the projective space P of H. And here H is the many-body Hilbert space. This is the usual formula, and you can basically replace this psi by GS of phi to get the capital G I'm talking about. This is the quantum metric in the twist angle space. Most remarkably, if I denote by this the expectation value on the ground state at phi, then I have that the quantum metric is precisely equal to the localization tensor I talked about before. Let us see how this emerges, at least intuitively. So if I take the thermodynamic limit, the position operator becomes a well-defined object, and it is essentially the derivative with respect to Bloch momenta k. So what I get is that the ground state obtained by changing the flux a little bit by delta phi is essentially obtained from the ground state at phi by multiplication by this unitary operator. Then this overlap has the form of a partition function where I insert this operator here in the middle to provide the new twisted boundary condition. If I take the second derivative of this partition function, or essentially the logarithm of this partition function, I get the localization tensor. Of course, I have to compute that delta phi equals to 0. Thus, the quantum metric in twist angle space is a measure of electron localization. For a family of quantum states, it is a known result that if the gap closes while changing some parameter, the quantum metric becomes singular. Let us give some intuition behind this. This is essentially tied to the fact that the family psi 0 of x, where x belongs to some manifold, and this psi 0 is a ground state of a gapped family h of x, where x belongs to some manifold, we have the formula that the quantum metric is given by the sum over all excited states of these overlaps. D of H is the derivative of H. The sum is over all excited states, and you have this squared of the energy in the denominator. This looks like perturbation theory, and it is no coincidence, actually. And so you see that as the gap to some excited state, let's say the first excited state, becomes zero, this here becomes potentially singular. As a consequence, if the system became metallic by tuning some external parameter, the localization tensor will naturally blow up. Okay, the Slater determinant that we had before for the ground state induces a similar form for the quantum metric as it did for the Berry curvature. So now you have that the quantum metric is equal to the sum, the quantum metric in the twist angle space, is the sum of the quantum metric, now not in twist angle space, but of course in momentum space. This is exactly analog of what happened with the Berry curvature. Here G is given by this trace formula. It is the quantum metric in momentum space. Of course, this trace accounts for the fact that the vector bundle has a rank different from 1. Essentially, this is a formula for a metric in a Grassmannian. The pullback. The thermodynamic limit now provides us with a flat metric, because now the components g mu nu of phi will be given by this integral, because this becomes a Riemann sum for this integral here. So g mu nu is now independent of phi. It is uniform, it is flat. A flat metric in the two torus is described by the Riemannian volume and by a complex parameter tau, as given like that. And this complex parameter lives naturally in the upper half space. If I take these two quantities, I can parametrize my metric as follows. And notice that the Riemannian volume appears as an overall factor, while the rest corresponds to the anisotropy of this metric. The complex parameter tau corresponds to the anisotropy of this metric. The complex parameter tau determines a complex coordinate on the torus given by phi equals to the first component phi1 plus tau phi2, and if I take this parameterization, this complex coordinate, I find that the metric G, capital G, is proportional to the standard metric on the plane with coordinate phi. It is conformal to the standard metric on the plane. This is an illustration of the complex torus of twist angles and fluxes, twist angles slash fluxes, and here you have the plane C and the complex coordinate phi given by phi1 plus tau phi2. To generate the twist angle space, you're instructed to identify phis that differ by translations on this lattice determined by 1 and tau, actually 2 pi 1 and 2 pi tau. Let us think about the physical interpretation. Notice that since the metric is essentially this correlation tensor, tau is naturally related to the anisotropy of position correlations and the Riemannian volume to the strength of these correlations. For instance, if I take the standard tau equals to I, corresponding to the usual lattice Z2, this gives that the off-diagonal elements are 0, so that the directions x1 and x2, they decouple. Now, this is not the full story, as we have to identify tau and tau prime such that they are related by this transformation here, where A, B, C, and D form an integer-valued invertible matrix. So essentially, this is a so-called modular transformation. So the reason that these correspond, that we have to identify tau and tau prime differing by these transformations, is that this corresponds to an observer which is choosing a different basis for the original lattice Z2 in real space, which differs by an invertible integer valued element. Essentially, this is a gauge degree of freedom of the theory. From the mathematics side, this corresponds to choosing a different element in the isomorphism class of the complex torus. Thus, in principle, if I change the insulator, we could move around the space of complex structures of the torus. This here is an illustration of the upper half space, and we have this fundamental domain of the action of GL2Z, where essentially this blue domain here, the fundamental domain, has a single representative of the complex structure modulo isomorphism. However, you still have to identify this segment here with this segment there, and also this segment there with this segment here. This basically means that this is not the full story. You still need to mod out. This space here, the quotient space of the upper half space by the invertible group elements, integer valued matrices, is not a manifold. It is actually a space with the structure of an orbifold. And there are these orbifold points, tau equals to I and tau equals to e to the 2 pi I divided by 3, that have increased symmetry. Now I will relate tau to the low energy theory near a quantum phase transition, and I will talk about the geometric character of tau. Suppose we are given a single particle Hamiltonian and that two levels cross generically at a critical momentum kc by tuning a parameter m, and the choice of m is not naive, it's because I want to think of m as a mass, to a system, to a value critical m, mc. By a shift of variables, we can assume that kc is equal to 0 and that mc is equal to 0. The two-level crossing can be then described in a neighborhood of k m equals to 0 by a 2x2 low-energy Hamiltonian of the form linear combination of Pauli matrices sigma 1, sigma 2, and sigma 3. Essentially, the coefficients a, b, and c have to satisfy this relation in order for some Jacobian matrix to be non-singular. In the absence of symmetries, this case is completely generic in the sense that other types of crossings, like quadratic band crossing, can be adiabatically connected to this one. Let us define new momenta, Q, which are related to K by this matrix A of coefficients, A, B, C, and D. Then, in these new variables, the Dirac Hamiltonian I defined before assumes the isotropic form Q1 sigma 1 plus Q2 sigma 2 plus M sigma 3. The new momenta Q are explicitly violating the dual lattice 2 pi z2, since if I shift the original momenta by a reciprocal lattice vector, the new momenta will not get shifted by a reciprocal lattice vector unless AK is in the reciprocal lattice, and that means that A has to be in GL2Z, meaning that A has to be an invertible integer valued matrix. Let us compute the quantum metric, or at least try to do so. To compute the quantum metric in twist angle space, I need to compute the following integral. But for that, I need an expression of g mu of k. And I can do this in a neighborhood of the critical point k equals to 0, which in the q coordinates, the new momenta coordinates, assumes the following form, plus something which is regular, in the sense that the first term, as I approach the critical point q equals to 0 and m goes to 0, goes singular. One can see that as m goes to 0, the most relevant contribution to the integral should be given by a small neighborhood of k equals to 0, which we're going to take as a disk, an open disk. The transformation Q goes to AK is linear and has a constant Jacobian. And by the way, it's different from zero because I assumed the generic crossing. Therefore, we can safely perform the integration in Q and then go back to the original coordinates. This actually corresponds to changing the phi coordinates appropriately. The quantum metric will then assume the form, in matrix form, this term here plus regular terms. Through a conformal transformation, I can pass this element here, this multiplicative constant, to that part here. And we see that since m goes to 0, this thing blows up. I can make the regular part go to 0. And actually tau, given as that ratio of matrix elements, will go to this form here in terms of the coefficients a, b, c, and d. But more precisely, this will be given as a ratio of two complex numbers, which correspond to the columns of the matrix A. Okay? If it wasn't clear, lambda is a bit arbitrary, but it has to be small. It is the neighborhood of k equals to 0, which contributes the most to the integral, because it's near the critical point. Okay? So lambda essentially is small, but otherwise arbitrary. So what you see is that the columns of this matrix A, which define the new coordinates, give you two complex numbers, which generate a lattice, which determines tau at the gapless point m equals to 0. So this formula here is only valid for the critical point m equals to 0. If A is in GL2Z, meaning it's integer valued and invertible, then we end up with the lattice Z2. And tau is equivalent to the standard complex structure on the torus, tau equals to I. We also remark that the Riemannian volume goes like that. And you see that as m goes to 0, the Riemannian volume blows up and the system becomes gapless. Therefore, the Riemannian volume is responsible for the singularity in the localization tensor when m goes to 0, meaning when the system became metallic. It is important to compare the quantum metric to the Berry curvature. Let us see. The behavior of the momentum space quantum metric associated to the Dirac point that I just described is given as follows. This should be compared to the behavior of the momentum space Berry curvature, F, which has this behavior. There is a striking feature that you observe. Let me talk about it. A transition in which m changes sign, m goes from minus m to m, is known as a band inversion. It involves a change in the topology of the occupied bundle E, the Bloch bundle, because the change of the Chern number is naturally associated with the change of the mass, m, the change of the sign of the mass. This signature is present on the local form of F because this is odd under m goes to minus m. Notice that as I take m goes to minus m, this goes to minus f. And it is natural to expect because the first Chern number is proportional to the integral of f on the Brillouin zone. Since f is odd under m goes to minus m and g is even, we understand that the quantum metric on twist angle space, as well as tau, they do not distinguish between topological phase transitions in which the Chern number goes plus 1 or the Chern number goes minus 1. In other words, they are the same for them. Okay? Note, however, that the quantum metric in flux space captures the gap closing point through the Riemannian volume, and tau captures the information of the anisotropy of the local low energy theory because it's simply a function of the matrix A. This emphasizes the topological character of the flat curvature F, mathcal F, versus the geometric character of the quantum metric in twist angle space. I'm going to give you an example which I came up with to be able to generate all possible complex structures. It is a modified massive Dirac model. We consider spinless fermions with a pseudo-spin internal degree of freedom, so that the tight binding model is given as follows. Again, sigmas are the Pauli matrices, 2 by 2. And here, A and B, A belongs to, is a real parameter, and B has to be greater than 0. The usual massive Dirac model is recovered for A equals to 0 and B equals to 1, and it is familiar to both high-energy physics and low-energy physicists because its low-energy theory has the familiar 2 plus 1 dimensional Dirac Hamiltonian form with a mass m. It is basically Q1 sigma 1 plus Q2 sigma 2 plus a mass times sigma 3. The model has a topological phase diagram which is independent of A and B. The topological phase diagram is determined by determining the first Chern number of the block bundle, because the isomorphism class in the smooth category of vector bundles over the two torus is precisely given by the first Chern number. So C1, the first Chern number of E, is 0 if the absolute value of the mass is greater than 2. It is plus 1 if the absolute value of the mass, if the mass is between minus 2 and 0. It is minus 1 if m is in between 0 and 2. Don't forget that C1 generates the transverse Hall conductivity of the plateaus, transverse Hall conductivity plateaus. And here you can check that the critical points are precisely minus 2, 0, and plus 2, where the phase transitions occur. If you use the previous results I gave you concerning the low energy theories, you can show that in this model, tau equals to A plus IB for the critical points plus or minus 2, and tau equals to minus A plus IB for the critical point MC equals to 0. Moreover, if I tune in the parameters so that I'm in the usual massive Dirac model, isotropic, meaning that A equals to 0 and B equals to 1, I recover the standard complex structure on the torus, tau equals to I. If I put A and B arbitraries in the model, I recover the whole space of complex structures. So this model is rich enough to capture all the complex structures I want. Okay, let us move on to the conclusions and some outlook. We have shown how in two spatial dimensions the anisotropy of the localization tensor is related to a complex structure tau over the twist angle torus. Tau is geometric and not topological. Therefore, it is sensitive to adiabatic perturbations. Tau is finite, even when undergoing a phase transition, where the gap closes, and therefore I'm going through a metallic phase. Tau is intimately related to the anisotropy of the low energy theory, the Dirac theory, near the critical points. Indeed, at the critical points of phase transition, tau is solely determined by the low energy theory. The complex structure tau and the Riemannian volume V are physically sensible gauge invariant observables, which completely characterize the localization tensor. Tau can be defined. Okay, this is a subtle point. Now, I've done everything, this discussion, in the setup of quasi-free fermion theories, meaning that the Hamiltonian was quadratic in the fermion creation and annihilation operators. But I can define it in the presence of interactions if I have a gap condition and if I have a family of ground states parametrized by fluxes. In that scenario, my family, GS of phi, better not be trivial, because if it is trivial, constant, that is, the metric will automatically be degenerate because the metric involves derivatives of this family. In the interacting case, G will not generically be flat, because we won't have the Slater determinant formula. The procedure to determine tau is to determine a flat metric in the conformal class of G, which involves solving a partial differential equation for the conformal factor, which enforces the Ricci scalar to be zero. And this is possible because of the genus of the torus. Tau and V will no longer, in general, completely specify the localization tensor, since the latter will not be flat. In the presence of translation invariance, this can also be seen as a measure of how interactive the system is. Namely, if I fail to describe miserably the localization tensor completely through tau and V, essentially I'm having fluctuations of a quasi-free fermion description. If you want to read through the details, you can check my paper. A big thanks to João, Zé, Thomas, Nathan, Nicola, Rafaela, and Roger for fruitful discussions. Thank you, and stay safe.